Well, let's remember what the standard error was back in Chapter 8. In the previous chapter, Chapter 8, we presented the statistical procedures that permit researchers to use a sample mean to test hypotheses about an unknown population mean. These statistical procedures were based on a few basic concepts where we summarize. A sample mean is expected to approximate its population mean, and this permits us to use the sample mean as a test of the hypothesis about the population mean. The standard error provides a measure of how well the sample mean approximates that population mean. In other words, it allowed us to calculate Z. So specifically, the standard error determined how much difference is reasonable to expect between a sample mean and a population mean, and you'll see the way we calculated it. This is where this is all headed. I had the population standard deviation, and I had radical n for the size of the sample. The new formula that we're headed to is very similar, and here it goes. The calculation of t must be used when s is known and that population standard deviation is not known. And by the way, what's s? The sample standard deviation, as we'll see here shortly. The shortcoming of using a z-score for hypothesis testing is that the z-score formula requires more information that's available. Specifically, a z-score requires that we know the value of the population standard deviation, or the variance, which is needed to compute the standard error, but in most of the situations, this is not known, just in real world. In fact, the whole reason for conducting a hypothesis test is to gain knowledge about that unknown population, of which we are most often ignorant. The situation appears to create a paradox. You want to use a z-score to find out about an unknown population, but you must know about the population before you can compute that z-score. Fortunately, there's a simple solution. When the variance or standard deviation for the population is not known, we use corresponding sample values in its place, which will be the sample standard deviation, or however we can get to it, which might be the sum of squares of the variance, but for our purposes, I always give you the sample standard deviation. So there's some routine math calculating that sample variance that really resembles the population variance. So here goes. In Chapter 4, the sample variance was specifically developed to provide an unbiased estimate of the corresponding population variance. You remember this whole business of n minus 1. So we divided the sum of squares by n minus 1. Now, in our situations, we're not going there. We're not going to get into those fine distinctions of calculating all this. I'm going to give it to you. I'm actually going to give you the standard deviation. But you'll recall that the formulas for the sample variance and the sample standard deviation were as follows. And in fact, here's a simpler rendering. When I give you the sample variance, it's just so much easier to handle it this way, which is the sample standard deviation right here is just the square root of the variance. It really annoys me, frankly, when they list it this way. This is literally equivalent, I know that, but why not just take the simplest rendering possible? And that's what I would prefer. That's what I'll do on the handful of problems that we have. I think we have 5 in this video series. And in all of them, I will just simply list S. We don't even have to worry about the antecedents being the variance and all this business. But for the record, I'd like it to be known that to get the standard deviation, I just take the square root of the variance. And that's what we'll need to calculate the standard error, which frankly is our focus anyway, right? So then I move on to this estimated standard error. Now you'll notice this is what we had in Chapter 8, and this thing looks a heck of a lot like it. Like how? Well, you remember here was a formula, right? I calculated the standard error, which was literally the standard deviation of the distribution of sample means, like this. The estimated standard error is merely this piece of cake. And this, of course, stands for the estimated standard error, which is merely the standard deviation, which I'm going to give you all the time. I don't want to take an indirect path and give you something different. I'll give you S every time, divided by the square root of n. So you can see it's very, very, very similar. Some routine math for that estimated standard error that really resembles the standard error. It's the exact same thing, and I always pledge to take the simplest rendering possible. This is literally correct over here, but I just like to avoid it. I think one mistake we stats professors can make is giving too many options. Why assume that everybody recognizes formulas to be equivalent? Let's just not go there. Let's take it simple, 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 and stick with that. This is the simplest rendering possible, particularly if you give the lowercase s, which is the sample standard deviation. So you have my pledge that I'll always do that. But I hope you're impressed so far that this thing looks a lot like this thing, and all I have to do is substitute. No big deal.